Good morning. We're going to get started with our 11 a.m. press conference, X marks the spot, NASA's OSIRIS-REx sample collection site announcement. Today here we have Glaze from NASA headquarters, Dante Lauretta from the University of Arizona, Daniella DellaGiustina also from the University of Arizona, and Michael Moreau from NASA Goddard Space Flight Center. I'll turn it right over to Glaze to get us started.
Great. Thank you so much. We're really excited to be making this announcement here today. But before we start getting into more information about the OSIRIS-REx mission and the site selection today, I thought I'd give you just a little bit of the context for how OSIRIS-REx fits into NASA's planetary program and why we explore small bodies and asteroids like Bennu. So there's many different populations of small bodies in our solar system. And when we talk about small bodies, we're talking about asteroids and comets, moons, small moons of some of the planets, dwarf planets, protoplanets. There's a diverse set of these objects out in our solar system, and you can find them in lots of different places. So for example, for asteroids and these very, very small bodies, we find them in the near-Earth population, those that occasionally fly near Earth. We find a bunch of those objects in the main asteroid belt between Mars and Jupiter. There's a whole class of these objects that are found in the leading and trailing orbits of Jupiter called Trojan asteroids. And then out beyond Pluto, we have the objects in the Kuiper belt. And each of these objects are telling us different parts of our solar system history. By going to each of these different populations and different areas in the solar system, we can learn a lot of information from these small bodies that are actually remnants that have preserved some of the very earliest history of the solar system. So when we're studying the small bodies, there's a variety of research themes that are consistent across all of the different missions that we have that are exploring different small bodies. And OSIRIS-REx is actually hitting 5 of the 6 major themes, and 3 of them in a really major way. I like to say that OSIRIS-REx is a real triple threat because it really gets at some of these really, really big questions. First and foremost, as I said, Bennu, we believe, is an extremely old object from the earliest times of the solar system, and so it retains some of that evidence and some of the information that can tell us about early solar system formation. We also believe that the surface of Bennu contains materials that include minerals that are hydrated, formed with water, perhaps organic molecules. And so by studying those materials and bringing them back to Earth, we can better understand how those materials may have been delivered to Earth and may have been the seeds for formation of life on Earth. And then finally, as we start to think about human exploration beyond Earth and beyond our Earth-Moon system, we've started to think about how might we use and take advantage of the materials that are out there in the solar system. Are there resources that are available on these asteroids that might be of use to us in the future? So as we're going forward, these are the types of questions that we're trying to answer, and in particular by doing sample return. And of course, sample return is an incredibly important part of what we do in planetary science. We can look at things from a remote vantage point, from Earth-based or ground-based telescope systems, or with spacecraft like the OSIRIS-REx spacecraft itself, taking remote measurements. But until we can take those samples and get them in our hands and bring them back into our laboratories here at home, there's really just no substitute for that. Back here, we have incredible capabilities in our laboratories, state-of-the-art technologies, and the abilities to really study those samples in detail. And not only can we study them today, but we'll preserve large amounts of the sample for future generations so that we can use new technologies and new laboratory facilities that we haven't even dreamed of yet. So that's why the sample return is such an important part of our program. So now turning to a little bit more towards OSIRIS-REx in particular, the team has spent an incredible amount of time studying the surface of Bennu over the last year, poring over the details of the surface and exploring and looking to find the best site for taking that precious sample. And you're going to hear a lot more about that here today, but I thought I would share with you just a little bit about the process. Once the team had looked over all of the various sites and looked at all the various parameters, the size distribution of the materials on the surface, how safe it is to go to the surface to collect the sample, all of those competing factors, they weighed in and came up with a recommendation for what they believe was the best site for taking a sample. And it wasn't a straight shot. It's a very complicated picture, and there's a lot of different factors that people weigh in different ways. And so once the team had made their selection of Nightingale, which you're going to hear about more in a few moments, they brought that selection to NASA headquarters, and the PI, Dante Lauretta, made the case and all of the different arguments for the different factors for safety and sampleability. They made that case to our Associate Administrator, Dr. Thomas Zurbuchen. And as we all listened to that presentation, they made a very compelling case, and of course Thomas concurred with the recommendation, which is Nightingale as the primary site and Osprey as the backup site. And with that, I'm just going to hand it over to Dante, who can tell you much more about the various sites.
Thank you, Lori, for that introduction and background. And I do want to thank Lori and Thomas Zurbuchen and the entire team at NASA headquarters. It's been a great partnership. We go to them with our thoughts and our approaches, and we've had a lot of feedback and really a very productive working relationship. It's been a real pleasure to work with the agency and support this amazing exploration. So we're looking here at the global mosaic of the asteroid, and this is really just one example of the large number of data products that the team has put together to characterize the entire surface of this asteroid. We also have a fantastic 3D topographic model that was collected with our laser altimeter from the Canadian Space Agency. Of course, the images that went into building this mosaic were done with our OCAMS instrument from the University of Arizona, and then we've also relied heavily on the OVIRS instrument from the Goddard Space Flight Center and the Otis thermal emission spectrometer from Arizona State University to give us a very diverse picture of the asteroid surface and to allow us to interpret the chemistry, the mineralogy, the size grain distribution, the geology, the gravity field, and all the other parameters that go into determining where we think we can safely collect a high science value site from the asteroid surface. So after an extensive down select process, we got to our final 4. All of them had their merits and their challenges. As Lori mentioned, this wasn't an easy decision. We deliberated back and forth, and I could tell you on the eve of the decision, I was torn, especially between the Nightingale and the Osprey sites. Those two were really neck and neck right down to the wire. And at the end of the day, we went with the Nightingale site for a variety of reasons. Taking a look at it here, one of the things that strikes me right away, so just pay attention to the scale bar here. In fact, I'll click to the next one, which shows the same site, but with this outline of the spacecraft. So X marks the spot. That's the site that we're targeting to collect the sample from. As you'll hear from Mike Moreau, my colleague at Goddard Space Flight Center, we're going to be doing a lot of analysis to see where we're most likely to touch down, but where all the possibilities are based on the details of what happens during the sample collection sequence. It's really a very nice fine-grained patch of sampleable material. And what we're really looking for is grain sizes on the order of 2 centimeters or smaller that we can ingest into our TAGSAM sampling mechanism. And my colleague, DellaGiustina from the University of Arizona, will tell you about the processes that we went through to characterize those grain size distributions and make that sample site selection. You can also see that it's kind of a tight fit. Right, we've got to get this spacecraft into a relatively small crater. That spacecraft's about 6 meters wide with the solar arrays extended. That's what the 2 squares are on either side of that, and that's the main spacecraft bus there, into a 20-meter crater. And that may not sound bad, but you also got to remember we're 250 million kilometers away from Earth. The one-way light time is tens of minutes. Everything happens autonomously on the vehicle, and the spacecraft has to make a lot of intelligent decisions about whether it's safe to continue down to sample collection. So this is our 3D view. So what we've done here is we've taken that 3-dimensional topographic data and then we've overlaid the high-resolution mosaics on top of that to get a real assessment of the Nightingale site. So I'll focus on a couple of the key features. First of all, the crater itself. We do see abundant evidence of material that we can ingest, but there are some substantial hazards even within the crater itself. In fact, this ring of boulders right here is something we want to make sure we steer clear from. To me, the most impressive feature is this wall of rocks on the eastern edge of the crater. I call the big sharp-pointed one Mount Doom colloquially, just because it reminds me of that feature from literature. And it is the most challenging part of getting into this site. We're going to come down on a vector that's normal to the crater surface, but we aren't sure what's going to happen when the spacecraft contacts the asteroid, and it may, in fact, experience some torques or some forces that tip it over a little bit. And it's going to fly away from the asteroid surface along the angle that it achieves after that rate stops changing. And so we got to make sure it doesn't tip over and then fly away in a direction that's going to impact that large set of rocks on the eastern side. And there's also a similar set of hazards over here in the northwestern part of the crater. What really drove the decision for me here on this site was the scientific value. One of the characteristics of Nightingale is that it's a high latitude. In fact, it's the highest latitude of the final 4 sites at 55 degrees north. That means it stays relatively cool relative to the sites at the equator like Osprey and Kingfisher. And cool is good because we're interested in organic material and we're interested in hydrated minerals. And those appear to be in higher concentrations in this site, probably because it's cooler and those are more well preserved in this region here. It also is one of the most finest grain areas on the surface, overall characterized by a low albedo or relatively dark material, which we think is linked to the presence of carbon and is consistent with our detection of organic material in this region. So for a variety of scientific reasons, I felt that this was the right site. It does have some hazards associated with it. Mike's going to talk about how we're dealing with that. That's what he's responsible for. And so they gave me their confidence that they can get into this site, or at the worst case, they can keep the spacecraft safe with some software on board that would recognize a hazard and then wave off or back away if the spacecraft determined it was actually going into an unsafe contact condition with the asteroid surface. If we do that, then we are maybe disturbing the site to the point where we can't go back there because we're going to fire thrusters, moving material around the surface. So Osprey is our backup. It's a similar sized crater. You can see the outline of the spacecraft here. It doesn't appear to have as much fine-grained material as Nightingale does, but we still believe there is some sampleable material in this crater. But what makes this distinctive, it doesn't have those large hazards around it. So we could tip over farther on this site and still fly away safely from the asteroid surface. So in general, it's a site with fewer hazards, meaning that if it's a good choice for the backup. So we go into Nightingale. I'm confident we're going to get a sample from there, but this is NASA. We always wear our belt and suspenders to make sure we achieve mission success. And Osprey is the site that guarantees contact with the asteroid surface and collecting something from the asteroid. So with that, I'm going to turn it over to Danny, who's going to talk to us about the extensive amount of work that went into mapping the asteroid surface and assessing its sampleability.
Okay, thanks, Dante. So just to provide some perspective in terms of what it took to get to the point where we were capable of making this decision, before we even could evaluate the presence of candidate sample sites on the surface, we had to first map the asteroid. And so this mosaic right here represents a map that we created at the very beginning of this year of 2019. And since then, we have acquired approximately 25,000 additional images from the OSIRIS-REx camera suite, which is built by the University of Arizona in pursuit of examining potential sample sites on Bennu. And the net result of all of that work are our prime and backup candidate sample sites, Nightingale and Osprey. So just looking at these sites in a little more detail. So over here on my left, you can see Osprey, and on my right, you can see Nightingale. And even though these look like seamless photos of both of the sites, these are actually image mosaics that are composed of about half a dozen images that we created in an effort to further characterize and map the presence of particles that we can collect on the surface of the asteroid. So the science team this past summer and moving into the fall just did a tremendous amount of work characterizing all of the candidate sample sites in an effort to figure out which site has the best scientific value and which site has the most material that we can collect, what we've been referring to as sampleable material. And so to do this, using these mosaics, we examined all of the particles or rocks and pebbles on the surface to map out what can we sample here versus what can we probably not sample. And the end result of all of that tremendous effort is our sampleability map. So we had dozens of science team members working to characterize these sites, count particles, count boulders at the sites, and we were also aided by citizen scientists who came in and augmented our efforts, and in particular the CosmoQuest program helped with this assessment. And so after a great amount of detailed characterization, these are the maps that represent where we believe sampleable material exists. Blue indicates a high level of sampleability, whereas red represents material that is not sampleable by the spacecraft sampling mechanism. And as you can see on both of these maps overlaid on the image mosaics, there is much more blue or much more sampleable material at Nightingale. And that was one of the primary reasons that Nightingale was chosen as our first sampling site. Osprey, however, still has plenty of sampleable material as well, so we feel like it will be a great backup if we go in for a second attempt. And with that, I'm going to go ahead and turn it over to my colleague Mike Moreau that can speak to some of the challenges ahead.
So thank you, Danny. So now that we've got an introduction to the primary and backup site, I'm going to talk about the sample collection sequence and some of the changes that we've had to make to how the spacecraft will perform TAG in order to have a chance of navigating into some of these precarious sites. So the first graphic shows an animation of the trajectory that the spacecraft's going to follow during the TAG sequence. It begins with the spacecraft in an orbit that's about 1 kilometer from the center of Bennu. The spacecraft will fire its thrusters and depart from orbit, and that will set up a descent to the location of the TAG site over the sunlit side of Bennu. As the spacecraft nears the surface, it's going to perform 2 maneuvers that precisely target the TAG site. The first burn, called checkpoint maneuver, is done at about 100 meters altitude, and the second burn is called the match point maneuver, which kind of sets up the terminal velocity to contact at the TAG site at the right location. OSIRIS-REx will contact the surface with a sample collection mechanism called TAG-SAM. And TAG-SAM is mounted on the end of the robotic arm on the spacecraft. It's the only part of the spacecraft that will touch the surface. The spacecraft will only make contact with the surface for a few seconds. It's kind of like it's bouncing on a pogo stick. It'll make contact with the surface for a few seconds, fire its thrusters, and then back away. When contact is detected, it will fire a nitrogen gas bottle, and that will stir up some of this fine-grained regolith and churn it and capture it in the sample collection ring. So that's the technique that will be used to collect a sample. The final point about this animation is that when the spacecraft is on its transit to the TAG site, it's going to be taking images with a navigation camera. Those images are processed on board the spacecraft and are used to update the position and the velocity as it goes through TAG. That's important for both refining those final 2 maneuvers to target precisely the site, and it's also important for keeping the spacecraft safe, as I'll talk about a little bit later. So if you're watching the animation closely, you can tell it was created before we saw what Bennu really looks like. At the final point where the TAG-SAM touches the surface, you see this nice flat area that doesn't have any rocks in it. But we now know that there's no place like that on Bennu, not even close. All of the TAG sites that we were considering in the process didn't come close to meeting that requirement. And so that created some significant challenges for the team. We really had to not just think about how we would do TAG differently, but how we would pick the site and what data we would use to pick the site. So my next graphic shows the Nightingale site again, and it has some overlays to help you have some context for what's going on the site. So I'll just point out a couple of things. So this is showing essentially a parking lot graphic, so you can see the size of a typical car overlaid right on the center of the TAG site. Now, our original requirement for delivering the spacecraft to the surface was that we had to land within 25 meters of the targeted location. So that 25-meter radius or 50-meter diameter landing zone is shown by this orange circle here. So it should be obvious to you from the 3D animation you saw earlier that we can't let the spacecraft touch in some of these places. That would be a problem. So we are actually targeting a spot that's much smaller, and the blue region, the blue circle gives you an idea of about what the precision of our delivery that we've gotten to with the spacecraft. But we still have to be prepared if something were to go a little off with our delivery. We need to be prepared to keep the spacecraft safe if it drifts out into this region. So that is the challenge that we're facing. And in response to this challenge, the engineers have come up with a couple of different innovations and that have actually increased the capability of the spacecraft. First of all, the members of the navigation team working with members of the flight operations team have really sharpened their pencils and improved the precision of deliverability. That's how we got from 25 meters down to an ellipse that's 5 to 8 meters or so for deliverability, about 5 times better than what we were expecting. But one of the major changes that was made to the system itself was to switch to an onboard image-based navigation process called natural feature tracking, or NFT. This was what I alluded to earlier, where the spacecraft is taking images, processing those, and using them to update its knowledge of position and velocity on board. NFT allows us to do that with great precision. The other piece that leverages NFT is something we're calling a hazard map. And that's what's depicted in this graphic here. The hazard map is created on the ground based on the engineer's assessment of the topography, uploaded to the spacecraft, and then in conjunction with the onboard knowledge, it's able to keep the spacecraft safe. So the hazard map works in a way analogous to a traffic light. You can see the red, yellow, and green on this map. If the spacecraft, when it predicts the contact location, determines that we're coming down on a green spot, we will keep going and contact the surface and fire the gas bottle. If it predicts that we're coming down on a red spot, we'll put on the brakes and do a back-away maneuver and be able to recycle and try again. If it comes down in one of these areas that's yellow, it's very much like a yellow traffic light. You might be able to cruise on through it, but out of caution, we're kind of too close to the hazard, so we'll brake in that case anyway. So the combination of improving the performance of the system, coming up with some new capabilities on board the spacecraft, those are the steps that have been taken to allow us to get into what is otherwise a pretty precarious site on Bennu. But this does introduce the concept that we may not be successful on our first tag attempt. I've alluded to the fact that there could be a wave off. That would be a case where we make it to a distance of about 5 meters before we back off. There's also the chance, as Danny alluded to, that we could contact the surface successfully, fire the gas bottle, but if we're unlucky and touch in one of these areas that doesn't have very much sampleable material, we may not collect an adequate sample on the first attempt. So my final graph shows the schedule that we are going to be working on now that we've achieved the site selection milestone. So over the next couple of months, we're going to be conducting a couple of close reconnaissance flybys. The first will be at an altitude of about 500 meters, and the second will be an altitude of 250 meters. This will collect the final high-resolution imagery that will be used to finish building the maps we use for navigation and confirm the assumptions about the sampleable regions of the tag sites. Later in the spring, we're going to conduct a series of 2 rehearsals. The first rehearsal will take us down through the tag sequence to a distance of about 50 meters from the surface. The second will take us down to a distance of about 25 meters. Once we've completed those 2 activities in the June timeframe, we will have exercised nearly all of the capabilities on board the spacecraft that are needed to successfully tag, and we will know with confidence that we can actually touch the surface safely. So we are targeting August 25th of 2020 for our first tag attempt. If we are unsuccessful, we expect to have other opportunities to tag in the fall of 2020. But we think Nightingale gives us the best chance to be successful on that first attempt. So I wanted to conclude my prepared remarks just saying that all of the work that has gone into the site selection and kind of revamping our whole strategy to do TAG has been an incredible team effort. And you've heard about the University of Arizona. I mentioned Lockheed Martin, members of Goddard Space Flight Center, Kinetics Aerospace, and there are science team members from organizations all over the country and, in fact, the world. All of those team members and organizations have worked together through this site selection process and through this engineering process. And it's taken people stepping up and sometimes contributing in ways that they might not have expected they were going to need to contribute in order to make this possible. So it's really been a great effort, and the team is very excited now that Nightingale has been selected to be able to move on and focus all of our energy on preparing to tag at Nightingale. So thank you for your attention, and I think we're ready to take questions now.
We'll now open it to questions from reporters in the audience.
Harvey Lyford, freelance. It looks very fragile. How does it get back to Earth and through our atmosphere? And how much dust or pebbles or whatever will you actually have to work with?
Okay, I'll take that. The only part of the spacecraft that will return through the atmosphere is a sample collection, sample capsule. It's a capsule that was used, similar design on the Stardust and Genesis missions that we've repurposed for OSIRIS-REx. But there is a 2-year journey to take the spacecraft back to the vicinity of the Earth, and in the final hours, that capsule will be ejected, re-enter the Earth's atmosphere, and come down in an Army base in Utah, where we will retrieve it. In terms of the mass of the sample, the system was designed to collect up to 2 kilograms of material. Our minimum success criteria is that we return 60 grams of sample.
Paul Vusin from Science Magazine. Dante, I remember when we talked a few years back, you mentioned the question of the type of surface that could be sampled. Obviously, you haven't had quite a luxurious sampling selection, but can you talk a bit about why you're targeting recently exhumed material, and was there anything, was there some debate over stuff that was space weathered versus that?
That's a great question, and it's interesting when you look across Bennu. It does seem like the fine-grained material is concentrated in these smaller craters, and so we're thinking that maybe there is a subsurface layer on this asteroid, that the fine-grained material is kind of percolating down through these larger boulders, and that's why the surface appears to be so rough and rugged and bouldery. That's still speculation at this point, but it does seem to be consistent with the observation that the fine-grained material predominantly is in the centers of these smaller craters. The only site that's different from that in the final 4 is the Sandpiper site. And that is part of a much larger crater. It's about a 50-meter crater in the southern hemisphere of the asteroid. When we talk about space weathering, that's a very active debate on the science team right now, and it really comes down to, does this material get more red or more blue? Generally, Bennu is a blue asteroid. It's a B-type asteroid. It reflects more solar radiation at the shorter wavelengths than at the longer ones. The site, like Kingfisher, is one of the reddest sites on the asteroid surface. We think that means it's fresher, or at least it's finer grained. Sandpiper is different. It had a bluer characteristic to it, and maybe that meant it was older. That would be consistent with it being part of that larger crater. But none of that is known right now. That's really just what we're trying to understand from the geology and the color and the spectral properties. And really, that's why we're bringing back a sample, is to really test that kind of assumptions. The good news is space weathering is interesting, and a lot of team members want weathered material, so they'd be very happy if that was the case. My instinct tells me Nightingale looks like a fresh crater, just from its morphology. It looks like it overprinted maybe a couple of other smaller craters, and so I think it's the best chance at getting that pristine, carbonaceous material that's the prime objective of OSIRIS-REx.
Yeah, hi. Mike Wall from space.com. Just a quick question about how much kind of margin for error you guys have on the sampling runs. I mean, how much nitrogen gas do you have? How many times can you blow that? And say you do it the first time and don't get enough. How many times can you go back in and do it? I mean, I assume there are 4 sampling sites, so you could theoretically go down 4 different times, but do you have enough nitrogen gas to fire 4 different times?
Yeah, so we have 3 gas bottles. There's 3 times where we can touch the surface and actually register that surface contact and fire one of those gas bottles. I think in the end, we're really going to be limited based on time. It takes time to recycle and prepare to go back again. And, you can imagine us having, several attempts of going through this process. The other consumable is fuel. It takes fuel every time we do these maneuvers, but that's really a minor concern because we have, it takes only a very few ounces of propellant every time we do one of these maneuvers because of the microgravity environment, and we have hundreds of meters per second of delta V margin. So it really comes down to the time it takes to assess the success of our sample attempt and the preparations for getting ready for the next one. But we believe we can turn that around in a period of about 9 weeks. I guess as one other point I could make is that we do have a deadline. The window for us to depart Bennu to bring the sample back to Earth opens in March of 2021 and closes in the April to May timeframe of 2021. That's kind of the nominal window we're targeting. But that gives us several opportunities to make multiple attempts, maybe go back to the same site more than once if we need to.
Further questions from reporters in the room? I think we have a couple questions on chat.
For Dante, Emily Lakdawala from the Planetary Society asks, are you seeing differences in composition between the fine-grained material and the rockier material on Bennu? And what do you think the fine-grained material is made of?
I think Danny might be best qualified to answer that.
Sure, I'd be happy to answer that. So at present time, we are seeing differences in color, and although composition can be one way to interpret differences in color between the different sites, there are other physical mechanisms that might give rise to different colors, such as grain size. And so we are planning to do further characterization to kind of break that debate of the sites. But I will say that Nightingale, our prime candidate site, it is much redder than all of the other sites, and we are interpreting that at present time as an abundance of fine-grained material. We have done some characterization with our hyperspectral instruments, such as the OSIRIS instrument provided by Goddard Space Flight Center, to look at the more detailed compositional details. And that has at least initially given us maybe some hints that there's more organics at that candidate site as well. So again, it's a very compelling site from a science perspective, and that was one of the reasons it was chosen as the first site.
And then Rick Lovett, a freelancer, asks, how tall is Mount Doom? They appear to be small, jagged features by earthly standards.
Yeah, so Mount Doom is about 7 meters above the local terrain, but the bottom of the Nightingale crater is about 3 more meters down, so there's about 10 meters of relief. If you go back to the parking lot graphic that I showed, what we're trying to do is essentially navigate the spacecraft down to a location that's the width of a couple of parking spaces, and it's just a few steps away from a 2 to 3 story tall building. Pretty exciting.
Last call for questions from the room. No one? All right, well, let's thank our panelists. We'll probably be here for a few minutes if you have additional questions. We were resuming at 1:30 for an update from the Juno program.